Hi, welcome to my presentation on our research project on in-class performance prediction. My name is Noah Hunt-Isaak, and I did this research with Peter Cherniavsky, and we were advised by Dr. Mark Snyder and Dr. Josefa Rungwala. We did this research as part of an REU in educational data mining at George Mason University over the summer of 2019. The motivating problem behind this research project is notoriously high rates of dropout and failure in university-level introductory CS courses across the United States. According to studies, this rate is around 30%, failure rate, that is, in CS introductory courses around the nation. We found very similar rates at George Mason in CS 112, which is the introductory computer science course at that university. The idea behind this project is to develop an early warning system and grade prediction model using data mining techniques, which will allow us to accurately predict student success in a course midway through that course so that struggling students can be flagged for further intervention. We note that intro courses tend to be quite large, which can make it difficult for professors to identify students who are struggling. Using a predictive model, this can be made much easier for the professor, and we can more accurately identify students who are struggling and provide them additional support. The data set that we had access to was 2 years of data from the intro course CS 112. Data, and this is over 2 semesters, so 4 classes in total. Data included gradebook data, such as homework, exam, and lab scores, polling data from the in-class polling system called Pitania, which was used in each class to students could actively respond to questions electronically, and we have access to whether or not students answered questions and whether or not they got those questions correct. And finally, we had data from the online textbook, ZYBook. We have interaction logs with that textbook, which includes submissions of problems and timestamps to those submissions. A key step in any data mining project is feature extraction. So, in our feature extraction, we aimed to capture insights into a student's performance beyond what could be seen simply in the gradebook. Here are some example features that we engineered, which we think could give our model an edge over one which was simply based on using gradebook data. So one such feature is punctuality. So this is a simple measure of how early, on average, is a student of submitting their assignments relative to the due date. This isn't something that's going to show up in the actual grade, but it might be a relevant indicator of success. Another such feature could be reinforcement. So this is basically from the online textbook logs. We can see whether or not students were re-attempting problems that they had already done correctly. So for example, if a student re-attempts problems leading up to an exam in an attempt to study, this might be a good sign. Another such feature is engagement. We can look at their Pitania participation, whether or not they were answering questions, whether or not they were getting those right, and how this changes over time throughout the course. For example, if a student initially has high engagement, but that engagement begins to drop off, that might be a sign that the student might be in trouble. We used Python's machine learning library, sklearn, and the implementations of a variety of regression algorithms which are within that library in order to make our predictions. We then used cross-validation to compare the results of the different algorithms to see which ones work best, and to try and make the best predictions we possibly could. For our tasks, we were aiming to predict two different things mainly: final exam scores and final overall grades. We saw these as being the two most relevant indicators of student success in a course. We used a variety of algorithms, including linear regression, lasso and ridge regression, the support vector machine, and a variety of ensemble algorithms. The metrics we used for measuring the success of our algorithms were mean absolute error, root mean squared error, and the R2 score. Here's a table containing some results comparing the effectiveness of a variety of different algorithms according to our three metrics and our two tasks. Looking at the table, we see that the support vector machine, when using a linear kernel, was among the most effective of our algorithms at both tasks and by all metrics. We also see that the ridge regression algorithm was very effective for predicting final course score. In this graph, we look at our predictive accuracy when using the best regression algorithms from the previous table over time in a course. We can see that at the midway point of the course, around 6 to 10 weeks, we're able to make fairly accurate predictions of both final exam score and final course grade. We can also analyze the regression coefficients in order to see which features correlate most strongly with predictive accuracy. In this graph, for example, we see the regression coefficients when attempting to predict final exam score from about 6 weeks into the course. We note that the highest feature with the highest correlation is this one, T1, which corresponds to the score on the first test. So it's not surprising that your score on the first test in the course will predict strongly with your final exam score, since, in effect, the ability to test well should suggest the ability to test well in the future. So when looking at some of the other features, we can get some more useful information out of this. For example, we see that Lab 6 over here has a stronger predictive accuracy than most of the other assignments, even the other labs, which, according to the grade, the impact they have on the grade directly, should be equivalent. However, we see that this assignment is a much better predictor of final exam score than any other. Thus, you can imagine a situation in which a student performs well on the first 3 labs or so, but then struggles on more important labs in terms of predicting final exam score. According to their gradebook, they might not notice that they're in trouble, but our predictive model might be able to catch this fact. This can also be useful for the professor in the long term in terms of course design. For example, they might spend more time in the future prepping students for Lab 6, or they might change the content on the other labs to more accurately reflect what will ultimately be on the final exam. In conclusion, we see that data mining methods can be used to create an effective predictive engine for in-class performance. This can be useful as an early warning system for identifying struggling students. Furthermore, regression coefficients can be analyzed to gain insights into course design. This can help both the professor and the students in the long run. You can see our paper for more details, or feel free to ask us any questions you might have. Thank you for your time.